Hello, welcome to lecture V3d. In this lecture, I'll present the full dilithium signature scheme. I'll conclude by describing the dilithium parameter sets in FIPS 204, and I'll summarize the dilithium details that I omitted in this chapter. Here is the notation we've been using for dilithium. The new items are d, the number of bits dropped from coefficients of polynomials in the public key component t, and omega, the maximum number of ones in the hint bit vector h. The ML-DSA 87 parameters have d equals 13 and omega equals 75. Key generation for the full dilithium signature scheme differs from the version without t compression as follows. I'll just highlight the differences. After computing t in step 5, Alice applies the power 2 round function to the coefficients of polynomials in t and obtains polynomial vectors t1 and t0. When d equals 13, which is the case for the ML-DSA 87 parameter set, the coefficients in t0 are 13-bit integers, whereas the coefficients in t1 are 10-bit integers. Compute tr, the 512-bit hash of rho and t1. Alice's public verification key is comprised of rho and t1. Her private signature key is comprised of rho, k, tr, s1, s2, and t0. Signature generation in the full dilithium signature scheme differs only in steps 6f and 7 from the scheme without t compression that was presented in V2b. In step 6f, the signer verifies that the infinity norm of the polynomial vector minus ct0 is less than gamma 2. If it is, then the signer uses makeHint to compute the hint vector h, and checks that the number of ones in h is at most omega. The restriction on the number of ones in h is to minimize the signature size, since the signer needs to include the vector h in the signature. So now there are 4 requirements in step 6f. Z should have infinity norm less than gamma 1 minus beta. Recall that this requirement is needed for security to ensure that Z does not leak any information about the secret S1. Second, R0 should have infinity norm less than gamma 2 minus beta. Recall that this requirement is needed for signature verification to work, whereby the verifier is able to compute W1, the high bits of W. Third, minus C times T0 should have infinity norm less than gamma 2. This requirement accommodates compression of the public key component T, whereby signature verification can be done without knowledge of the low-order bits T0 of T. And fourth, the number of ones in H should be at most omega. As mentioned, this requirement is to minimize the signature size. If all these 4 requirements are met, then the signature gamma, comprising of tilde C, Z, and H, is returned. Here is how signature verification in the full dilithium scheme differs from the scheme without T compression that was presented in V2b. The hint vector is included in the signature, and the public key is comprised of rho and t1 instead of rho and t. The verifier checks that the number of ones in the hint vector is at most omega. If not, he rejects the signature. He computes the hash tr of the public key using t1 instead of t. Finally, in step 6, he computes the commitment W1 primed by first computing AZ minus CT1 times 2 to the d, and then uses the hint bits to compute the high bits of AZ minus CT without knowledge of T0. I'll let you check for yourself that signature verification works. The argument is essentially the same as the one presented in slide 104, but now incorporates the hint bits. FIPS 204 specifies 3 parameter sets for dilithium. These parameter sets are ML-DSA 44, ML-DSA 65, and ML-DSA 87. The parameter sets are intended to provide at least as much security as SHA-256, 192-bit AES, and 256-bit AES respectively. Notice that all 3 parameter sets have the same values of Q and N, so they use the same polynomial ring. Even though the polynomial rings are the same, one gets increased security levels by increasing the size of the matrix A. So 4 by 4 for the first parameter set, 6 by 5 for the second parameter set, and 8 by 7 for the third. The 2 digits in the parameter names are the KL values. These parameters, and also the values of the other parameters, were carefully chosen to balance security, public key and signature sizes, and the expected number of iterations in signature generation. For the ML-DSA 87 parameters, the public key size is 2,592 bytes. 32 bytes for the 256-bit string row, and 2560 bytes for T1, which is comprised of 8 polynomials, each having 256 10-bit coefficients. The signing key size is 4,896 bytes. The coefficients of polynomials in S1 and S2 are 3 bits in size. This is because eta 2 is 2, and so 3 bits are needed to represent the 5 possible values -2, -1, 0, 1, and 2 for a coefficient. The coefficients of polynomials in T0 are each 13 bits in size. This is because D is 13. The signature size is 4,627 bytes. Coefficients of polynomials in Z have size 20 bits. The maximum possible absolute value for a coefficient in Z is gamma 1 minus beta. Recall the requirement that the infinity norm of Z be less than gamma 1 minus beta. So, the total number of possible values for a coefficient is 2 gamma 1 minus 2 beta minus 1, which is slightly less than 2 to the 20 for the ML-DSA 87 parameters. Thus, a coefficient of Z can be represented using 20 bits. Lastly, the hint bit vector can be represented in 83 bytes, as I'll show next. The hint bits for a polynomial is a 0,1 vector of length 256. This is because there is 1 hint bit for each coefficient of the polynomial. This gives a total of k hint vectors, 1 hint vector for each polynomial, for a total of 256 times k bits. Call these vectors h1, h2, up to hk. A hint vector can be represented by a binary string of bit length 256. Then, the k hint bit vectors have a total byte length of 256 bytes when k equals 8. However, since at most omega equals 75 of the 2048 bits are 1, it's more space efficient to record the bit positions of the 1s in H. Suppose that U of these bits are 1, where U is at most omega, the upper bound on the total number of 1 bits. The dilithium standard represents the 1 bits as follows. Let Y be an array of omega plus k bytes, which are initialized to 0. For the ML-DSA 87 parameter set, the array has length 83 bytes. byte number omega plus 1 records the number of 1 bits in the vector h1. Byte number omega plus 2 records the number of 1 bits in the vectors h1 and h2, and so on up to byte omega plus k. Then, byte 1, byte 2 up to byte u record the bit positions of the 1s in h1, h2, and hk in that order. Given the array y, which has byte length omega plus k, one can easily reconstruct the hint bit vectors h1, h2 up to hk. I'll leave that as an exercise for you. Here are the signing key sizes, the verification key sizes, and the signature sizes for the 3 dilithium parameter sets. Key sizes and signature sizes are significantly larger than for RSA and elliptic curve systems. When migrating from RSA and ECC to Kyber and Dilithium, these increased sizes will be challenging to deal with in some scenarios. Recall that each iteration of the main loop in signature generation has 4 requirements. The first check is necessary for security. Let P1 be the probability that the polynomial vector z has infinity norm less than gamma 1 minus beta. Recall that z equals y plus cs1. Let u be a coefficient of cs1, where u is between minus beta and beta. Then, the corresponding coefficient of z is in the open interval from minus gamma 1 plus beta to gamma 1 minus beta, provided that the corresponding coefficient in y is in the open interval from minus gamma 1 plus beta minus u to gamma 1 minus beta minus u. This interval has length 2 times gamma 1 minus beta minus 1, which is independent of u. Hence, the probability that the coefficient of z is in the desired interval is 2 times gamma 1 minus beta minus 1 divided by 2 gamma 1. The denominator is 2 gamma 1 because the total number of possibilities for a coefficient of y is 2 gamma 1. Since there are 256 times L coefficients in Z, P1 is this probability raised to the power 256 times L. The expression simplifies to this, which is roughly e to the power minus 256 L beta divided by gamma 1. The second check is needed for signature verification to work. Assume that the 2 gamma 2 low bits of W minus CS2 are uniformly distributed. This is a reasonable assumption. Then, the probability that a particular coefficient in W minus CS2 is less than gamma 2 minus beta in absolute value is given by this expression. Here, the denominator 2 gamma 2 plus 1 is the total number of possibilities for the 2 gamma 2 low bits of an integer. And the numerator 2 times gamma 2 minus beta minus 1 counts the numbers that are less than gamma 2 minus beta in absolute value. Since there are 256k coefficients in W minus CS2, the probability P2 is given by this expression, which simplifies to this, and is roughly e to the power minus 256k beta divided by gamma 2. The third check is that the infinity norm of minus CT0 is less than gamma 2, so that the verifier can compute W1 primed without knowledge of the low-order bits T0 of the public key T. And the fourth check is that the number of 1s in hint vector H is at most omega. This probability is claimed to be high, greater than 0.98, although there is no formal analysis of this claim as far as I know. Assuming that the four requirements are independent of each other, the probability that they are met is P1 times P2 times P3. Thus, the expected number of iterations in signature generation is 1 over P1, P2, P3, which is approximately 1 over P1, P2, since P3 is close to 1. So the expected number of iterations is given by this expression. You can check that for the three sets of parameters in FIPS 204, the expected number of iterations is 4.25, 5.1, and 3.85 respectively. Compression of the public key component T does not affect the security claim for dilithium. Hence, dilithium is existentially unforgeable against chosen message attack, assuming that the decisional module learning with errors problem and the module SIS problem are intractable, and where H is modeled as a random function. My description of dilithium omitted some details, which you can find in the FIPS 204 document. These omissions were the use of shake to define the expand A, expand S, and expand mask functions, the sample and ball routine, formatting for bit strings and byte strings, an optional upper bound on the number of iterations in signature generation, and the number theoretic transform for polynomial multiplication in the dilithium ring of polynomials. The dilithium NTT will be the topic of the next video. The primary references I used for the dilithium videos are first, the research paper that introduced dilithium. This paper was published in 2018 in the IACR Transactions on Cryptographic Hardware and Embedded Systems. Second, the dilithium specification that was submitted to NIST. You can find this document on the Crystals Dilithium webpage, which also includes links to software and other resources. And of course, I used the recently published NIST standard FIPS 204. As with Kyber, the design of dilithium was influenced by the works of many cryptographers in the past 3 decades. You can trace back the main contributions from the references in these 3 sources.